Speed sensing of hydroelectric turbines has always been a critical function of turbine governor and control systems. The earliest speed sensing methods were mechanical in nature, using flyweights and speeder springs because the control systems were completely hydraulic and mechanical in nature. The advent of digital computers has revolutionized turbine control systems, added new capabilities, and required advancements in sensor and signal conditioner technologies. More precise speed sensing has been achieved by using the generator's output voltage like a tachometer signal. The subject of this video is the PT interface signal conditioner developed to convert the generator output voltage to a pulse train suitable for inputting to a turbine governor and control system. Two signal sensing elements are used to compute power output of the generator in watts: the voltage or potential transformer and the current transformer. For short, these are called the VTs or PTs and CTs. The generator output voltage or potential is tapped off and connected to the input of the PT interface. The first generation PT interface signal conditioner used by Woodward Governor Company consisted of a dropping resistor and two back-to-back rectifier diode pairs to clip the signal at 2.4 volts peak to peak. This signal was input to the proximity pickup input of the digital speed sensor. When the exciter is on, the 110 volt AC input from the potential transformer to PT interface clipper circuit provides a strong, reliable speed signal to the governor. The most beneficial use of this premier PT interface signal is for synchronizing the unit to the grid before closing the main breakers. When the exciter is off, the residual magnetism in the generator rotor still provides a sufficient speed signal with the original clipper PT interface, but only when unit speed is above 70%. Below 70% speed, the residual output of the generator was too small for the proximity pickup input of the digital speed sensor on the governor to read, so the speed indication drops to 0. Proximity pickups provide a good pulse train output, but it is difficult and expensive to provide a wraparound gear for a turbine shaft, and manufacturing irregularities and runout of the gear teeth and the valleys between them will produce frequency modulation that makes unit synchronization more difficult and imprecise. The compromise in this situation was to use the proximity pickup below 70% speed and then to switch over to the PT interface output above 70% speed. In 1991, Woodward engineers were installing a new digital governor on a hydroelectric turbine for Hydro-Quebec when a shortcoming of this rudimentary first-generation electronic PT interface caused a problem. A wraparound gear and proximity pickups were not used on this governor installation, so the PT interface clipper signal was used to control unit braking application. A bad choice, as it turned out. As the unit wound down from the first test run, when speed dropped below 70%, the speed signal became unreadable by the governor proximity pickup high-speed counter input. The governor logic saw this as speed of 0 RPM, and the brake control logic applied full force to the brakes to hold the unit in place to prevent creeping, or very slow rotation that can harm the bearings. Applying the brakes at full force at 70% speed was beyond their capability, which caused a great deal of noise, vibration, and smoke. A great wailing and gnashing of teeth went up as the workers ran for cover. It was also said that there was copious profanity in French. After the dust settled, it was decided that a new approach should be tried. Woodward Governor's electronic engineer, Dave Cornegay, designed a new amplified PT interface circuit for this application that amplifies the low voltage signal generated by the residual magnetism in the rotor up and attenuates the full 110 volts AC signal down, both to a 24 volt peak-to-peak pulse train for the proximity pickup of the governor. This new device expands the operating range of the PT interface from 0.2 to 180 volts AC across a frequency range of from 6 to 180 Hz. This new PT interface module has seen wide use over the last 20 years. With the demise of Woodward's Hydro division 10 years ago, this circuit became unavailable to the ex-Woodward Governor engineers who scattered to other companies to continue working at designing hydro governors. In order to establish a new source for this circuit, while working at L&S Electric in 2001, Dave Cornegay set up a contract manufacturing arrangement with Actuation Test Equipment Company so that this superior device could be used in L&S Electric's governor control systems. Since then, over 500 of these signal conditioners have been supplied to L&S Electric without a single electronic failure. Earlier this year, a design improvement was made to solve an instrumentation problem with a horizontal Francis wheel turbine in northern Canada. The unit had no brakes, so the turbine speed wound down very slowly, taking almost an hour to coast to a stop. As the speed got down to about 3%, where the residual magnetism in the rotor produced an AC sine wave with an amplitude slightly below the threshold voltage of the PT interface, a spurious signal was getting through to the high-speed counter input of the governor PLC. The problem was traced back to the high-frequency energy that was coming from the 4 kHz switcher battery chargers in the plant. When the turbine was spinning at about 3% RPM and the input waveform from the residual magnetism output of the generator was close to the threshold voltage, the 4 kHz riding on top of it would cause the PT interface to flicker in response to the 4 kHz noise momentarily each time the generator's output voltage was at the threshold. It was easier to design a new PT interface circuit than to replace all of the signal wire with enough shielded cabling to cure the problem they were having. A new hysteresis circuit was developed with a threshold limit that blocks any response to input signals with amplitude less than 75 millivolts to cure this problem. More recently, this hysteresis circuit has been applied as the solution to a signal noise problem on a pair of Francis turbines in the southeastern United States, where signal crosstalk has been getting into the PT interface signals intermittently for over a year. A few months ago, a new 480-volt power conductor for a backup generator was pulled through the cable trough, at which time the crosstalk became more intense and started causing more serious problems with operation of one of the units. When the unit's start relay closed, but before the unit started to roll, the output of the PT interface jumped up to 100% speed, 60 Hz, momentarily. This signal existed until the unit started to spin and the normal signal from the generator's residual magnetism appeared and took over as the predominant signal. When the 100% speed signal was present, the exciter control relay closed automatically because its logic saw that the unit was up to speed. The magnetic field developed by the exciter current in the rotor grabbed onto the poles in the stator like a stepping motor's holding current, making the unit harder to roll when the gates were open slightly. One potential problem with this situation is that the rotor could be pulled off axis by the magnetic fields and scuff the stator, requiring disassembly of the unit to make repairs. As the unit's speed increases, the voltage generated by the residual magnetism becomes the predominant signal into the PT interface, and then the pulse train output to the PLC high-speed counter input becomes a proper speed signal for the unit. Diagnostic troubleshooting found that the signal wires for the PT interface are unshielded, which was allowing crosstalk from other power-carrying conductors to get into the input signal of the PT interface module. While the unit was still stationary, the crosstalk signal was measured at 106 millivolts ACRMS before the unit started to spin. One fix that was considered was to modify the governor software so that its program logic could ignore the incorrect signal based on other conditions. This idea was discarded because the unit would need to be recommissioned after a software program change. Another plan was to replace all of the speed sensor signal wires with shielded cables, also an expensive proposition. As the saying goes, timing is everything. The new PT interface with hysteresis module, which had just become available, is an ideal solution to this problem. The new circuit is designed to ignore low amplitude noise on the PT interface input. This threshold can be adjusted during assembly by setting the gain of the hysteresis amplifier. For this application, the PT interface hysteresis circuit will be adjusted to block everything below 160 millivolts ACRMS. Installation will take place in about 4 to 6 weeks, at which time this video will be updated with the results.